Hi, Braze Oak students. For the next few days, we are going to be reviewing for the Common Assessment. And so today I am going to go over Unit 1. Each one of these videos, you'll get a recap of the key points. I'll go over them and show you a couple practice problems from that time. Then you're going to complete an extended practice on your own, and then you can submit that and move on. So in Unit 1, you really learned 4 things: the atomic structure and how to read it in the periodic table, how to calculate atomic mass and isotope abundance, electron and noble gas configurations, and how to determine the charge of an isotope. So let's get through those. In the periodic table, we have the different boxes that tell us different things about the element. Okay, and a few of the big ones that we'll need to remember is the top number is known as the atomic number, and this is also the number of protons within that element. Remember, each element has a unique number of protons, so if we know the number of protons, we know the element. It also tells us the atomic symbol. This is usually 1 or 2 letters that represent that element, and then there is the element name actually spelled out for us. Underneath that, there is a decimal number. This is the average atomic mass of that element, and I say it's an average because it's a weighted average of all the different isotopes, something we'll review in a little bit. The only thing that is missing from the periodic table is the number of neutrons, though you can kind of figure out the number of neutrons from the atomic mass. Again, something we will talk about further down. Another way we can represent elements is using isotope notation. Remember, in isotope notation, there's the element written big. There's a subscript to the left that tells us the atomic number, which is just the number of protons. And then there is the mass number on top, which tells us the number of protons and the number of neutrons. Do not get mass number confused with average atomic mass. Those are not the same thing. Mass number is just adding the protons and the neutrons, whereas the average atomic mass is calculated. And again, I'll show you that in just a little bit. Okay. So isotopes all have the same number of protons, but they have different numbers of neutrons. You may remember from right at the end of Unit 5, we talked about nuclear materials and how they are bombarded with neutrons to cause a chain reaction. So the different numbers of neutrons is what makes them isotopes. The name, the way we write it out is, if we were to put it like, say, in a sentence or something, is the element name and then dash, and then this is the mass number. So again, the number of protons plus the number of neutrons. So some examples of practice problems. We could give you an element written in isotope form and ask you a bunch of questions about it. Protons will always be the easiest. Protons are the same thing as the atomic number, and we know that the atomic number is the bottom number, so there's 17. Neutrons, we have to kind of figure out based off of the top number here. Remember, the top number is protons plus neutrons. And so we know that there are 17 protons, so we have to figure out how many neutrons there are to get us to 35. The easiest way to do that would be to just set up some subtraction. So we know there's 35 in total. If I subtract 17 of them, I have 18 left over, and that tells me there are 18 neutrons. So the rule is take the mass number and then subtract the atomic number. Electrons, we will always assume that these are neutral elements unless it says otherwise. And so in a neutral element, the number of electrons is the same as the number of protons. And so if we have 17 protons, then we will have 17 electrons as well. The atomic number, hopefully you remember, is the same as the number of protons. And the mass number is the one written on the top, that's 35. The element name, we would look it up in our periodic table, or you should know at this point that Cl is chlorine dash 35. So the way we write that is with the mass number after the dash. Okay. Next, we talked about how to calculate atomic mass in Unit 1, and this is one that gave some people a little bit of trouble because it does involve percents and multiplications. So I'm going to hopefully show you again, and it'll come back to you relatively quickly. So to calculate the atomic mass of an element, you determine any missing percents. You'll convert the percent abundance into decimals, multiply the masses times the decimals, and then add each of these terms together. Okay, so it's basically saying I have this much mass, and it makes up this much of the isotope, and then add all of that together, and I get the total. So, for example, in this first one, we're given a mass of 34.969 AMUs, and we know that if I were to have, say, a bucket of this stuff, 75% of it would have this mass, whereas 24% of it would have 36.966. So there are no missing percents. I know that because if I add up my 2% here, I get 100%. So I do not have to determine anything missing. Next, I'm going to convert it into decimal form. This problem is nice because it already has a table set up for me. And to convert it into decimal form, I just move my decimal to the left 2 times. So I get 0.7553. And then on the bottom, that would be 0.2447. So that's done. Next, I need to multiply the mass of each isotope times the decimal percent abundance. So I'm going to do mass times the decimal form. If you do not convert it, if you try to just multiply it by 75, you'll get a huge number, and not only will it be huge, it will be huge and incorrect. Okay, so let's pull up a calculator. Oh, ready to go. Come back. So the first one is 34.969. Oh, goodness. 34.969 times 0.7553. So that gives me my first mass, 26.412. Let's just do it this way. So 26.412 is this first one, 412. And remember, our units for mass in this case are AMUs. The second one, 36.966 times 0.2447 is 9.04 AMUs. So there's my multiplication, and now my last step is to just add these together. So I'm going to add 26.412. And that gives me a grand total of 35.458 AMUs, and that is done. So you just need to follow those steps, decimal form, multiply, then add, and you'll get it right every time. Let's check another one. A certain metal consists of 2 isotopes of masses 68.95 AMU and 70.95 AMU with abundances of 60.16 and 39.84% respectively. What is the average atomic mass of this element? And then this one wants us to use a CER, but I just want to show you guys the math for today. So we know we have 68.95 AMUs, and that has an abundance of 60.16%. The other one is 70.95 AMUs with a percent of 39.84. Let's see if there's anything missing. 60.16 plus 39.84 is 100%, so I don't have any missing percents. So next I'm going to convert to decimal by moving the decimal over 2 times. And now I just need to multiply the mass times the decimal form. So here we go. The mass is 68.95 times 0.6016. That's 41.48 AMUs. And 70.95 times 0.3984. That's 28.27. Okay. Make sure you round according to the problem. our very last step is to just add these guys up. So 41.48 and 28.27 give us 69.75 AMU. There you go. And so that was percent mass abundance. Next, we learned electron configurations. Electron configurations are easiest to understand based on the periodic table. So we learned all about the multiple orbitals, starting with the s orbital, which can only hold 2. So that is represented by the fact that in this column, or in these groups, there's only 2. Then there is the p orbital, and the p orbital can hold a grand total of 6. Then we learned about the d orbital. The d orbital could hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there is the f orbital, which could hold a grand total of 12 electrons. So if you wanted to name them, we learned that you always go in order: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So now we're right here, we're right at calcium. And then remember, when we get to D, we have to subtract 1. So it'd be 3d10. That would get us all the way across here. And now we're at gallium. We go back to 4, 4p6. So that gets us to krypton. Now we jump down to rubidium. So that's 5s2, 4d10, 5p6. So that got us all the way through row or period 5. And then when we get to 6, we start with 6s2. And then this is when we jumped down to our lanthanide series, and we had to subtract 2 from the energy level. So 4f12. All right. So a couple quick examples with that. Silicon, noble gas configuration. Let's start with the long form. Silicon is right here. It is element number 14. So that means I'm going to go 1s2, 2s2, 2p6, 3s2, 3p2. And to get it into noble gas configuration, we go up a period over to our noble gas. So that would be neon. And that takes care of the 1s2, the 2s2, and the 2p6. And so we just have to write 3s2, 3p2. That's all that's left over. So if I'm going to type this, it's going to be neon, 3s2, 3p2. 3s2, 3p2. Oh. And make sure that those are superscripts, not subscripts. And I broke everything. There we go. To count the number of valence electrons, we only care about the last period. And so the last period is 3. There's 2 in S, 2 in P for a grand total of 4. And I just realized I did not superscript this. There we go. Okay. Lastly, we looked at ions and ion configuration. We know that neutral atoms are unstable in most cases. They have the equal number of protons and electrons. They have a charge of 0, but they do not have a stable octet, and that should be ringing some bells. Remember, and the octet rule tells us that atoms with 8 valence electrons, or 8 electrons in its highest energy level, is going to be stable and unreactive. And then the one exception is helium, which can only hold 2 valence electron. So ions are stable in most cases because they have either taken or given away electrons in their highest energy level so that they have a stable octet, and they do not have a charge of 0. And so with that, that is a full review of Unit 1. Hopefully this helps, and then look forward to the rest of the reviews later this week.